Thank you, Mr. Chairman. Okay. Good morning to everyone. Well, I guess my introduction has already been made by Dan Gianola, so I will just stress some points here that the genomic evaluations are run officially or non-officially in a monthly or weekly basis for most of the countries. And there are a lot of different exchange of data within countries, but especially if we consider the exchange of data between countries. We have different genotyping platforms, Illumina, AFI, and so on. Different densities of platform from 3K to high density. In the next future, we will have next generation sequencing or genotyping by sequencing technologies. And there's also different genotyping quality of single animals. So the imputation in routine genomic evaluation will or actually requires now to be fast, accurate, and consistent. Otherwise, if you another option will be to have 40,000 processors like Gianola. So this has already been said before. I'll just go to the last consideration is that population structure in the Holstein breed, that is the population we consider. It's actually a good idea to use both sources of information, population information and pedigree. The method we are presenting here alternates between pedigree and population haplotype imputation. It handles multi-generational pedigree, inputting also many non-genotyped animals. It's optimized for medium to large hapsid families, so it's actually optimized for the dairy cattle. And it uses different length of segments. It uses fixed segments for the population haplotyping, and use variable length segments for the pedigree haplotyping for close relatives. And this actually allows to have better connection among adjoining segments in the population haplotyping. So here's a brief example of how it works. The initial step is actually the genotypic inconsistency should already been resolved, but anyway, it controls the software. It controls that there are not genotypic inconsistencies, and if it finds some, it just blanks, put to missing the genotypic information for the son. And then actually, the first step is to fill up the haplotypes using the pedigree. So it runs through the pedigree from the eldest to the youngest animal, initializing the haplotypes. So here's a brief example how it works. This first step, we have a sire and a dam. The genotype is 012 for the A allele, AB for 1, and BB for 2. So the next two lines are the paternal and maternal haplotypes. So it first initializes the haplotypes using own and parental homozygous loci. And then we have a fake, let's say, sons for these two scion and dam couple. The son 1 is sort of genotype for 54K, and the son 2 for a low density SNP chip. So the first example, the first SNP that I highlighted is quite simple to understand. So scion and dam are both homozygous for the second allele, so for the B allele, for example, and the son as well. So considering the step 1 that the genotypic inconsistencies were already resolved, this is quite simple that paternal and maternal haplotype for the son 1 are just 2. For the second son, this is, for example, a SNP that is not genotyped in the low density SNP chip, and it's quite simple as well because both of the B alleles come from the sire and the dam. In this example, the sire is again homozygous for the second allele, but the dam is heterozygous. So the son that is heterozygous gets the B allele from the sire, that's for sure. So it has to have the other allele from the dam, so on. Doing just this first step, it fills the paternal haplotype over an average of 66% of the genotype for the low density SNP chips. And then it goes to let's say the core part of the algorithm, that is an iterative part that considers both pedigree and population. It's actually divided into 3 sections. The first section is a pedigree, is the pedigree section that use variable length segments and actually search for grandparental origin of the haplotypes. This means that for example, the paternal haplotype of a son we try to match it with the paternal or maternal haplotype of the sire, and we do the same for the maternal haplotype on the dam. When it gets when it gets a match, it actually shares the information between both of them, so filling the blanks in between. The second part of the step 2 is the population part. Actually processes the pedigree from old to young and builds a list of population haplotypes. This is quite similar to what has been seen already in FindUp. And again, it shares the information once it finds a match. And the third step is actually sorting the population haplotypes by decreasing frequency of observations. And in our test, we run this 3 times, so this is 3 iterations. And there's actually a third step that we took this idea from FindUp. That is that steps 2 are actually repeated 3 times using a decreasing fixed length for the step 2b, so for the population segments. So in our test, we used the first segment of 300 SNPs, then we went to 150 and then to 75. In FindUp, there are actually 4. It starts with 600 and then goes down. The data we used was, actually what we did was compare this software to FindUp, the second version of FindUp from Paul Van Reyden. And we used the default options for the 2 software that were quite similar, except that in FindUp, there's an extra, there are 4, as I said before, there are 4 outer iterations. There are 4 step 3. The total amount of animals we used were 6,600 host and genotyped in 4 different Italian genomic projects. They were all genotyped with 54K version 1 or 2. Most of them were bulls. We had less than 500 cows. There was some editing involved. Individuals were already controlled, but for SNPs we did some editing on missing minor allele frequency and hard dividing equilibrium. Sex and BTA0 SNPs were excluded. So the total SNP retained were 41,500 SNP for the 54K. Then we took 1,171 samples and divided in 2 subsets. The first one just keeping the SNP that were in common with the 3K, and the other one with the 7K, so the low density. This 1,000 animals came from 50% of all the young bulls without genotyping progeny, mimicking the young animals, and 50% of all the cows available. So these are the results we got. First of all, there are 4 scenarios ordered by the amount of information of close relatives. The first scenario has sire, dam, and maternal grandsire genotype at 54K. And then goes down until animals with only the sire genotype at 54K. As you can see the numbers here, we only kept the scenarios with more than 50 observations. And the result actually says that I have to say something else about FindUp, that you see that the percentage of missing is 0. This is because there's a final run in FindUp that actually fills missing with more frequent genotypes. PedImpute doesn't have that feature. We decided to keep the missings as missing. But anyway, percentage of missing and percentage of errors actually decreased almost linearly with the augmentation of information of close relatives. So we go from 3.7% of error until 0.7. And the allelic square for animals with all the information of close relatives, so sire, dam, maternal, and sire genotype was around 98%. And the differences between PedImpute and FindUp were between 5% in the first scenario until almost 1% in the fourth scenario in favor of PedImpute. In terms of time, we just took the whole genome. We divided the whole genome into single chromosomes and then ran the imputation on single chromosomes using 6 processors, so 6 chromosomes at a time. And it took almost 3 minutes for PedImpute and 8 minutes for FindUp. The same things are seen in the 7K to the 54K. The percentage of error actually is even more reduced, but the differences between PedImpute and FindUp are actually lower. There's a maximum 1% of differences between the two software, And actually, in the third scenario, where sire and maternal grandsire are genotyped only, the find-up outperformed by 0.2%, so it was very little paired input. In terms of time of running, the differences were just minimal. So paired input was differences between the results I presented before. However, in the first scenario, we get an impressive allelic R-square of 99.3, 98% in find-up. When we got only the sire, the allelic R-square is 97, as we saw in the presentation of D'Angelo, for find-up, and 96 for 97 almost for paired input. So the conclusions are that, well, it has already been seen that the 7K chip is better in terms of imputation accuracy than the 3K chip. We saw that as well. And the differences between the two software were larger, imputing the 3K to 54 than the 7K to 54. And the paired input was, in almost all scenarios tested, slightly more accurate than find-up. And probably this could be biased results by the final most frequent fill-in, most frequent genotype fill-in in find-up. And well, in any case, paired input was faster than find-up. We also Anafi did some tests on using more animals than 6,000, and actually the ratio between the timings are actually maintained. And in any case, both of the software, because both of them use pedigree, are more accurate when more close relatives are genotyped and at higher densities. But anyway, paired input is not yet finished. There we are still working on that. For example, sex chromosomes are not yet considered, so you can impute sex chromosomes, but it will work as for the autosomal parts, while in find-up there's a special feature for sex chromosomes. There's no genotype ancestors accuracy evaluation, so we had the imputation on non-genotype animals, but we haven't assessed what the accuracy was in both programs. We only had 500 cows, so we need more cows to test that. And we haven't tested the imputation for higher densities, so from 54K to HD. And anyway, considering these results, this algorithm is currently being implemented in the Italian Host Association for the routine genomic evaluation. I'd like to thank people involved in these projects, Selmol, Prozo, Elic, and Indovanger for sharing the genotypes, and Paul Van Reyden for making the find-up source code available. And I think